oh. This.
Oh, great.
It's 1:30. We'll be starting the presentation from now. It's by Daniel Kirkwood, and the title of the presentation is Identity, Native Infrastructure Access Management. Please.
Awesome. Thank you very much. And welcome everyone to the session for this afternoon. I hope I haven't drawn you away from the open session next door, but we're here to talk about identity native infrastructure access management. Before I get to explaining what this topic is, very quickly, a little bit about myself. I've spent about 15 years working in technology with a few different focuses. The last 5 or so years, I've been working pretty exclusively with DevOps and DevOps teams, different tools in the DevOps toolchain, working with startups, working with enterprises that are trying to change all across the Asia Pacific region. Today, I'm the lead solutions engineer for APAC at Teleport. When I'm not working, I have 4 young kids that keep me really, really busy. They're at home this week in Sydney, Australia. So if I'm not with them, usually I'm running. And I love to run. It's been great this week, running a little bit around Tokyo. And yeah, it's a real privilege to be in the country and in the city and with you guys here for the session today and with everyone online. So what are we talking about today? What I'm hoping to do with this talk is to convince you about the importance of identity when it comes to infrastructure, access, and management. And I would hope this is something that you're thinking about already. Maybe it's the reason that you've come to this talk. But if not, I want you to think about what is the most precious thing that technology teams have to protect. For most teams that I talk to, this is data, right? This is the thing that would be very, very disastrous if it was out to get out of your hands. And when I look at the common data breach scenarios, a lot of them involve infrastructure. A lot of them involve engineering access to infrastructure and misconfigurations or poor security practice or policies that are misconfigured. So I think this is a really important area to think about for anyone who's in engineering, DevOps, platform engineering, software engineering. And this is why we're going to be talking about this today. I do have quite a few slides. I'm going to get to a couple of examples as to how I see good and bad practice in this area. And I'm going to show you a couple of demos as well towards the end. First, I want to cover just a little bit about, why are we in this situation? A little bit about the context around infrastructure access. And I won't go too historical here. To me, this is a situation that I see today. And I talk to a lot of teams about this. And it's all about the tension between 2 parts of a business. On the left-hand side, we've got technology teams, developers, infrastructure engineers, and the like. These are people who own applications, products for the business. They have a set of success metrics that are usually tied to those applications. How well does the application perform? How good is it at getting new customers, keeping customers, maybe the uptime around that application? And as we heard about yesterday from the keynote, a lot of teams have moved to a model where they're trying to evolve those applications relatively quickly, right? Change is important for keeping an application up to date. Change is important for responding to users' needs. So these products are constantly evolving. On the right-hand side, we have security teams. They own risk and compliance, strategy and tooling, and they have a completely different set of success metrics. And this means that these teams are always trying to push for visibility and control. And usually the teams on the right-hand side are trying to go a little bit slower, right? They don't really like a high pace of change because it introduces risk for the business. And I think the complicating factor that's part of this is that engineers over the past 10 years have been gaining a growing influence in the infrastructure realm. They have more control over infrastructure than ever before. And most of this is driven by cloud, right? Cloud adoption, the ability to spin up with a click or an API call, any of the supporting elements that you might need for your application. And the business is actually usually backing this side of the house as well, right? If they're trying to balance risk, it's a little bit different depending on the industry that you're in, but we've seen engineering teams given a lot of leeway to do what they like with infrastructure, as long as they're able to get a product out as quickly as possible. However, these teams cannot ignore access. Access is a foundation of security. And even if you're not security minded, these teams still need to think about, if I'm spinning up something like a Kubernetes cluster, how do I let my team access that thing? If I've got a fleet of virtual machines, how do people access that? How do we access databases? And whether you do that in a very secure way or a very insecure way, it's still something that you need to consider. And most of the time, I see this as a collaboration point between the two sides of the house, and one of the main sources of tension, right? Engineering teams don't like heavy security solutions because it takes a long time to get access to something. If they're trying to investigate a ticket, or if they're trying to try out a new idea, sometimes it can be really hard for them to even start because they can't get access. And this is what we're going to be discussing today. Now, I break access down into 4 components: connectivity, authentication, authorization, and audit. And this is what we're going to cover next. First, I want to talk about connectivity. This is secure communication over an untrusted network. Me as an entity, a client, I must be able to exchange messages with a server without fear of interception. And what I'm going to do with each of these components or pillars is I'm going to point out what I'm calling a legacy approach. This doesn't mean that this is an old approach or something that isn't used. This is actually what I see as very common practice, even though it doesn't really align with what we know to be best practice. And 2 legacy approaches that I see here. Number 1 is very aligned with a traditional data center approach, and it's all about the hardened security perimeter. So with a hardened security perimeter, everything that's outside the perimeter we say is external and untrusted. Everything that is internal is trusted, and therefore we don't think so much about the other tenets of security, whether that's authentication or audit. And you usually have a very defined entry point between the external to the internal network. Hopefully everyone here realizes why this is not a best practice approach. And I spoke earlier about common breach scenarios. I don't hear so much about breach scenarios that leverage this anymore, but a lot of them, let's say 10, 15 years ago, took advantage of the fact that once you're able to get a foothold within an internal network, propagating or moving sideways through that network is very, very easy because there were not many security controls on the internal side. Legacy approach number 2 is a little bit more aligned to cloud. And if we think about this idea of engineering teams who are able to consume cloud resources as much as they like, you end up with business units and projects who are spinning up their own little network segments in different cloud providers. And sometimes these people will follow good practice in terms of access. They will have a VPN in front of that network. They will use firewalls. They will use security groups. And they will try to do layered security within these isolated networks. The challenge is that as a business scales, often you need to work out how segment A talks to segment B, or how you give access to someone in another team to the application that you've built. How do you expose an API endpoint? How do you make sure someone can query the data that you've got so that they can run analytics against that? And what I see is that businesses that have grown kind of organically like this with the cloud end up with this very complex web of networks that are connected together. VPN to VPN, firewall to firewall, security group rules that needs to be translated. And there's a huge amount of complexity with this method when it comes to connectivity. Understanding which rules need to be changed to give someone access to a particular target is very network aligned, and there's a lot of error that can happen when you're reconfiguring this kind of connectivity approach. So the key thing to think about here is that really you should not have a trusted network. This idea of the hard shell with a squishy middle shouldn't exist. We shouldn't really trust anything, even if it happens to be on an internal network. And that means that we need to think about the other parts of access, authentication, authorization, and audit. And we need to think about how they can move away from the network layer. And we're going to be talking about how you might do that. Next, we have authentication. This one's fairly simple. This is how I prove that I am who I say I am. And it's probably a very easy one for people to understand because most people have some kind of username and password that they use to access things. The challenge with the username and password is that it's not really tied to your identity. A username and a password is really just a piece of data. That data can be exfiltrated, can be used somewhere else. Someone else can use your username and password, and they get exactly the same access that you've got, even though they don't really have your identity. And moving away from this is not impossible. You know, I think most people have multi-factor or even multi-factor when they're accessing different applications. And this is probably the most common approach that I see to moving away from this idea of having a password only. So combining a password, which is something you know, with something you have, like a token, a YubiKey, plus maybe something you are. Fingerprints could be one thing, a face scan could be another. The challenge with this, when you think about infrastructure, is how do you apply this to all of the different types of infrastructure that you've got? We're going to be exploring that as well. Next, we have authorization. So depending on who I am, authorization is a policy that says, okay, here are the things that you should have access to. This is where I really see things fall apart for engineering teams because most of them can't be bothered to set up any meaningful access policy. Either it's too complex to achieve, or more likely, engineers often trust other engineers. And you end up with a default access policy that just says, oh yeah, you're in my team, you and I should have the same access to things because we trust each other. You know, everyone should be able to do the same thing. So I do see very commonly default access policies that get applied to an entire team, maybe get applied to multiple teams, maybe apply to the whole organization, especially when you have companies that are growing very, very quickly. I also sometimes see network-based authorization. So this is a bit more of back in the kind of data center model where you can have security rules that just look at your source IP address and use that as a model to say, okay, yes, you should have access to a particular target or not. But whichever approach, the challenge with this is that it's often really hard to apply a policy that might exist somewhere. So let's say you've got a company policy that lives on a wiki somewhere that says developers should not have access to production data. Actually enforcing that when you've got a very complex infrastructure environment can be very, very difficult. And if you don't have strong identity, it's almost impossible to confidently apply this kind of policy. So the takeaway here is without identity, authorization is either complex or inconsistent. And finally, we've got audit. So this is understanding who has done what with as much detail as possible. This is another thing that I see kind of ignored when engineering teams are in charge of infrastructure. Audit is just kind of a cumbersome thing to deal with. If you're in a regulated industry, maybe it's something you can't ignore, but everyone who's outside of those regulated industries probably tries to avoid this problem, because with audit, you potentially end up with quite a lot of data. Even teams that I see do capture audit data, often that data is not particularly useful. If you're using a perimeter security approach and you've got that very defined entry point for your internal network, often once you cross that barrier, anything you do on the internal network, if there's not good identity internally, the audit data is just attached to an IP address or an IAM role. And effectively, it becomes sort of useless because it's very hard to understand who is attached to a particular action. I see teams that really struggle with correlation. So even if they have authentication at every single hop, trying to tie together different access events to get a meaningful audit is really, really difficult. And the challenge here is that it's not a problem that can be solved really with more data. Okay, if you don't have good identity, you're not going to get the effectiveness that you want out of your audit logs. And often teams aren't aware of this because day to day, they don't look at the audit log anyway. And it only becomes a problem when there's a breach scenario or there is an investigation and someone is screaming in your ear to say, tell me exactly who went into the production database that day. So similar to authorization, the takeaway here is that audit becomes more meaningful as identity becomes stronger. Something that some teams mention when I'm going through some of these ideas around access is that, well, we've got an identity provider. This kind of solves the problem, right? And the answer is it does, but only partially. An IDP or an SSO provider like Okta, Azure AD, OneLogin, Google Workspace are good. They're good because they centralize identity and they have a strong form of identity, which means any application put behind single sign-on is removing the individual secrets that users might have had to access that application previously. So this is good. It's also a good gate to apply other security controls. So multi-factor auth, other security checks like geolocation, device posture can be applied at this layer, which is good. However, we are talking about infrastructure access, and often these IDPs don't work really nicely outside of their focus area, which is web applications. So it might work nicely for HTTP, HTTPS apps, but when we're talking about other protocols you might be using for infrastructure, they're not always so easy to apply. Okay, so they're one piece of the puzzle, but they don't really solve the problem that we're talking about. So to get to the next layer of this, I want to talk through some examples. And there's a bit of a format to this. We're going to start with Kubernetes. And the first thing that I've done is look at the common options that I see for access to a Kubernetes cluster, broken down into the 4 pillars that we've just discussed. And this is not every option, but again, when I look at teams who are using Kubernetes in anger, this is what I see them using. And be aware that you're going to see differences here depending on whether you're consuming very vanilla upstream Kubernetes or one of the many kind of managed solutions or any other downstream product that's built on top of Kubernetes. Okay, so we have a list here of all the possible options. The next thing I'm going to do is overlay a bit of an opinionated rating system on top of this. I don't know how good the colors are on this projector, but we have red, yellow, and green. It's quite simple. And what I'm denoting here is that red options are things that you really shouldn't be doing. Green options are pretty good, yellow are okay. And I want to pick on a little bit of detail here. First of all, if we look at the connectivity options that you might have. And just to clarify here, when I say Kubernetes access, I don't mean your applications that exist in Kubernetes. I mean administrative access to the cluster itself. This is for people who need to interact with the Kubernetes API. They need to be running kubectl. They need to be changing resources within the Kubernetes cluster. And this could be users, or this could be a system like your CI/CD. So for connectivity, you could expose your Kubernetes API publicly, but no one is going to do this. And I would not recommend that you do this. And I don't see anyone doing this, which is good. So then your other two options are a VPN or a Bastion host. Each of these are okay, but they come with their own challenges. And actually, I'm going to run through a bit of a user flow that has both of these. So we'll see a bit of detail on there in a second. The second pillar there is authentication. Kubernetes, being a relatively mature project, has lots of options for authentication. There's really one that I would say you shouldn't use, which is a bearer token. And I don't see too many people using this. This is a static token with no expiry that gives you access to the Kubernetes API. I would definitely not recommend that. There are three options here, which you may sort of know the name of, but probably no one is using these directly. But they are utilized by a lot of the cloud options for authentication through to Kubernetes. So if you're using IAM auth to your Kubernetes cluster, it's going to be using webhook tokens in the back end. Nothing particularly wrong with using these. Each of them has their own kind of quirks and challenges. And mainly the problem that I see here is actually just complexity for configuration, especially if you're outside the kind of managed Kubernetes realm. What I want to do next is pick out one option from each of these approaches. We're going to ignore any red option and stitch this together into a common access workflow that I see. So in this case, we have a team that is consuming Kubernetes via EKS on AWS. And for this team to provide access to their clusters, they've chosen a VPN for connectivity. They're using IAM auth via webhook tokens. They're using Kubernetes native RBAC. And they're using Kubernetes native auditing as well, which they're forwarding through to CloudWatch. And if we look at the flow for this, the end user flow, if I am a developer that needs access to Kubernetes, what happens? There are a few steps. First, I'm going to authenticate to AWS, hopefully via single sign-on, and I'm going to receive some credentials associated with an IAM role. Next, I'm going to authenticate to a VPN. In this case, it's OpenVPN. I'll use LDAP or single sign-on again. And what I receive is an OpenVPN group, and I get an assigned IP address from a subnet associated with that group. Next, I can use my IAM credentials to auth to the Kubernetes cluster. I get a Kubernetes group and receive a kubeconfig. I can then use the kubeconfig to execute commands against the kube API, and everything I do is audited on the cluster and forwarded through to CloudWatch. And you might be looking at this and say, well, okay, that's fine. What's wrong with that? And there's nothing particularly wrong with this. And as I mentioned, this is something that I see a lot of teams doing today. But I would argue that this is not a great solution. And it is not identity native. So why? What are the challenges with this? Number one is the VPN. So we're taking a good identity source, let's say it's your single sign-on, and we're translating that to an IP address on a subnet, meaning that most of that good identity data is lost. The second challenge here is once I'm on that VPN, I've got access to the Kubernetes endpoint, which I want, but I've got potentially access to many other network endpoints as well, regardless of my identity. And the challenge here is that the authorization that we have on the VPN is fairly coarse-grained and it's network level. So if you want to get fine-grained with a VPN, you end up with a lot of subnets, which then becomes a huge networking challenge to solve. And it doesn't really relate nicely back to that idea of I have a policy around what developers should be able to access. The second problem with this method is around correlation. So let's look at that flow. We have AWS IAM, which translates my SSO into an IAM role. EKS will see my IAM role and translate that to a Kubernetes user role group. So when I'm looking at audit logs, I've got logs which will be attributed back to the Kubernetes group, which needs to be correlated back with the IAM role, which needs to be correlated back with the user. And I see lots of teams struggling to correlate logs in this scenario. All the data is there, but understanding how it all stitches together is not always clear. So this is good, but not great. What does great look like? An identity native solution here would look like this. First, I have no network connectivity. I have a Kubernetes API, which is essentially locked away from a kind of network layer perspective. And I have a way of brokering connectivity directly one-to-one between a user and a specific API endpoint. Next, for authentication, I'm going to use single sign-on. Plus, I might use something like multi-factor biodata or device attestation. Third, for authorization, because we're not going to be using network-based authorization, I've got a few options. For me to achieve the first point, which is brokered connectivity between a user and a cluster, I need to have some way of defining which groups get access to which cluster endpoints. Then I need a way of assigning, depending on who you are, which Kubernetes group you get. So we still want to use some platform native RBAC as well. And maybe I want to get down to the point of saying, here is the specific pod that different groups should get access to. And of course, for audit, this should be centralized and every single command should be attributed back to a single sign-on user. So in my mind, this is best practice for Kubernetes access. And you might be thinking this doesn't really align with any of the solutions that we've seen so far. I happen to work for Teleport, and this is exactly what we do. But we're not the only provider in this space. There are a few identity access providers out there which will achieve exactly this. But what I want to do next is show you how we do this with Teleport. So what I'm going to do first is log in to the Teleport service. To do that, I'm going to use my command line. Is that visible enough? Hopefully, yeah. Okay, cool. I've got a binary on my command line called TSH, which is the Teleport client binary. That's going to execute a single sign-on login. I'm going to be logging in as Arwen today. Arwen is a developer at my business called midearth.dev. Arwen has a password for Okta. She's also got multi-factor. So I've got a YubiKey plus a PIN. And once I've completed successful single sign-on, I now have access to the Teleport service. Now, I don't have any network access here, right? Like this is not a VPN. My EKS clusters actually have no allowed ingress. My security groups don't allow anything in. So there's no way for me to actually reach out to the Kubernetes cluster yet. But I can discover which clusters I can get access to. Now, there is authorization happening here as well. I have a policy that says anyone who is a developer, like Arwen, and this role is assigned from single sign-on because she's part of a developer group in Okta, gets access only to developer clusters. Whether those sit in AWS, GCP, Azure, on-prem, OpenShift, Tanzu, whatever you are running. So Arwen has access to a single cluster. which she can log into. And from this point, I can interact with my Kubernetes cluster. I've got MFA turned on per session here, and I'll talk about why this is important in a second. My cluster is back in Australia, so things might be a little bit slow. But here I was able to query the cluster and find out which pods are running on that cluster. I can also see my platform RBAC. So I can interrogate Kubernetes and say, what am I allowed to do against this cluster? And what we'll see is that I've got a view-only role, right? I've been placed into a view-only role by the access system. Okay, so you can see here, there is a lot of get, list, watch against the different Kubernetes resources. So that's Arwen's view of the world. She's able to log in once with single sign-on, find out available Kubernetes clusters, and connect to those clusters on her local CLI. I want to show you, to finish this demo, the other side, which is, let's say, the security team's view of the world, or the administrative side of this as well. And this relates back to audit. So I mentioned identity is important for a meaningful audit log. And what we can see here is every request that Arwen has executed against this Kubernetes cluster has become an audit log. These audit logs are attributed back to Arwen as a single sign-on user, even though the Kubernetes cluster itself isn't necessarily single sign-on aware. I can also see that she's executed a get against the API path for pods, and I can see exactly which cluster she's connecting to and which Kubernetes native RBAC is in place. And this becomes a single nice JSON formatted log, which really gets to the heart of who has done exactly what against my infrastructure. So thinking about the architectural diagram we saw earlier, how does that change for this kind of access? Really, we're replacing the VPN in this scenario. We don't like the blind, coarse-grained network access for a VPN, and I'm going to replace that with my proxy, which in this case is Teleport. This kind of proxy can also reach into the target systems to facilitate that one-to-one connectivity. I won't spend too much time on architectural detail here, but if you're interested in really how this works, please let me know. In terms of the user flow, we saw Arwen authenticate via single sign-on. We had optional MFA, different security controls at the single sign-on layer. And actually what happened behind the scenes there was Arwen received a certificate back on the command line, which was an artifact of her identity from single sign-on. So all of the metadata that I get back from Okta gets encoded within that certificate. All of my RBAC also gets encoded with that certificate. And certificates are really useful in this scenario because certificates have a built-in expiry date, right? There's no such thing really as a infinite certificate. Certificates can be revoked. Certificates can be tied to a specific host. And a certificate becomes the perfect replacement for a kind of secret that I might have used in the past. And we also get some good ways of protecting that certificate. So you notice that when I executed a command against the Kubernetes API, I had to do my multi-factor again. This is a way of ensuring that even if a smart attacker broke into my machine and took that certificate away, it would be effectively useless because anything they tried to execute against Teleport would require MFA. So the certificate was able to define that I should only have access to dev. Certificates have signatures as well. So if I try to alter that certificate, it becomes invalid. My Kubernetes groups were defined in that cert. And I was able to use that to get a kube config Now, you might also say that the kube config itself becomes a target. It becomes a secret that might be exfiltrated. And actually, in this case, because we're using teleport as a proxy, it's not. So the kube config doesn't point directly to my Kubernetes cluster like it might in a regular Kubernetes access scenario. It always points to teleport as the first hop. So if someone was to exfiltrate my kube config, their kubectl would try to communicate with our teleport cluster, and that user would not have an authenticated session, and the request would be dropped. So then number 3, I could execute my commands, and all commands were logged back in the centralized audit log. Now we've got a bit of time. I'm going to show you one more demo and then get to my final thoughts. I want to talk about databases very quickly. This is a less homogeneous environment to look at because there are so many different database engines out there. Most technology teams that I speak to will be using at least 2 of these database engines. Each of them has its own approach to data storage, replication, caching, availability. And of course, there are little subtle differences in terms of access as well. So if we take the same approach and look at the access pillars as it relates to database access and rate them, we can see some options here. If I was to pick on a couple, I've put username and password in red here. It's actually the most common access method that I see people using today for databases, which is kind of worrying. I've seen enterprises that have entire teams of DBAs whose only job is to respond to tickets to onboard and offboard database users. And they literally, that's their full time, is doing database user management. There are other solutions for authentication, but they're not necessarily friendly to use. Has anyone here configured Kerberos authentication for a database? It's not fun. X509 is good, but managing your own PKI can be challenging. IAM auth is really good, but your support is going to vary depending on which database engine that you're using. The other thing I want to point out is audit. And there are actually particular database engines that only include audit as an enterprise feature. So again, if you've got developers who are spinning up and spinning down environments, they're trying out different database engines, there may not even be an option for them to enable audit, depending on the database engine that they've chosen. So a number of challenges with the existing methods we have here for database access. So again, we're going to pick out a common access flow. Here's the architecture for that. The only real difference here is that I've picked a Bastion box instead of a VPN. And again, I would say that this is a suboptimal approach. I see lots of engineering teams using Bastion hosts exclusively. Now, some Bastion hosts, if they're under a managed kind of security solution, can be okay from a security perspective, but can be really, really difficult to use for an engineer. If engineers are managing these Bastion hosts themselves, often they just have a mess of SSH keys for accessing that first Bastion hop. And then you end up with this shared service with many users interacting at once with different targets. And the challenge then is that if I'm on a Bastion box and I need to authenticate again through the target system like a database, I'm kind of restricted as to the authentication options that I've got, right? It's kind of hard to do proper single sign-on from a remote Bastion SSH session. So again, people end up falling back to some kind of hard-coded credentials, some kind of username or password, or maybe getting access to IAM auth. And finally here, we again have that same problem around correlation, where if I'm running queries against a database, they will be attributed to a database user, which must be correlated with some kind of IAM role, which then must be correlated with an SSH user, which eventually then gets correlated back to the original identity. So I think you can guess where I'm going with this. Let me show you really quickly how this works, and then we'll finish up. Okay, so I'm already logged into my teleport service. I can check my access to databases as well here. And I've got the same RBAC in place in that Arwen is a developer. She only gets access to developer database instances and is only allowed to assume developer read-only roles on those databases. So she can then choose a user and choose a database to log in. She needs to satisfy MFA again. And she now gets generated a set of X509 certificates that are specific for this database access. And I can use those certs to either connect to the database on my CLI, or I can start up a local tunnel. So that second option there, I can set up a tunnel which might be used by a GUI client. So if you're running dbeaver or MySQL Workbench or anything like that, that can utilize Teleport as well. But I'll connect straight over the CLI. Okay, and I'm now in my database. So again, this is a MySQL RDS instance, which is completely private. There's no ingress that I allow to this database, but I'm able to selectively expose this endpoint to the right identities. And I can then do a bit of SQL. Oh, if I can type. And eventually I can get to some data. Okay, and I can finish my session. So very easy then for me to connect as a developer and find out exactly the data that I want to get to. Very easy for you to add another team into this system. It's all connected back to single sign-on. If you've got a data analytics team who suddenly need access to a particular database endpoint, very easy to do. Very easy to add a contractor team temporarily to get access to this kind of endpoint. And of course, everything is logged. So I'll just refresh the audit log. And we can see a lot of logs around what I've been doing against this database. In the interest of time, I'll just pick out one. Let's find my select statement. Okay, so we have a single sign-on user, even though the database is not really single sign-on aware. My user had to use multi-factor to access this database, even though the database is not multi-factor aware. And I can correlate that user with a specific time with a specific database query. Very, very useful thing to have. So I might skip through these. Again, if you're interested in the details as to how this works, please come and see me. But we're hitting time, so I'm going to wrap up. Final thoughts. I hope I've impressed on you the importance of identity for infrastructure access. An interesting thing that I've seen here is that I often talk to engineers that are interested in this, and they just have trouble getting around tough network rules, or they want to move really fast and can't be bothered managing an access solution per target. So they use a tool like ours. The nice thing is that once they implement that, they found that their security team is really interested as well, because once you're doing identity to target one-to-one mapping, you've pretty much reached zero trust, which is usually for their security counterparts, it's on their roadmap or it's something that they want to achieve. And I mentioned a few times that you're able to really, once you've got this solution in place, lock down things from a network perspective, turn off any network-based access. So that's an outcome that a lot of people achieve almost accidentally by moving to stronger identity. The next 2 points, you suddenly have a more meaningful access policy and a more meaningful audit trail. And finally, there's this idea of reduction of secrets, which, thinking back to the breach scenarios that I mentioned earlier on, definitely the amount of secrets that you've got and the lifetime of those secrets, how long do those secrets exist? can always be correlated with an increasing risk of a breach. Okay, so those are the things that I want you to think about. Think about if you're part of an engineering or an infrastructure team today, what is the complexity that you might have around managing access, especially if you've got different solutions for each of those pillars. If you've got different solutions depending on your particular infrastructure types or your particular environment or your particular cloud platform, think about the cost of that. And of course, think about Teleport if you'd like an easy solution as well. If you're interested, we do have an O'Reilly book, which covers a lot of what I've spoken about today in much greater detail. And we've got an open source project, which you can download and try yourself. I will be here as well, so please reach out if you've got any questions. And that's it. I want to thank you for your time and attentiveness. Thank you very much.
Thank you very much. I think we're hitting time. So if there's any question, then maybe we can find you.
Yeah, I'll be right here. Sure.
Thank you very much. Okay. So the next presentation will be starting from 2:30, another 15 minutes. See you again later.
Yeah, sure. Yeah. Actually, you have to join the Zoom room and present your screen there. Yeah.
原田です。どうですか？
OK です。ありがとうございます。
はい。
テスト、テスト。テスト。
It's time for the next presentation. The next presentation is by Mutia, and the title is How DevOps and the Everything as Code Paradigm Are Powering L'Oreal Beauty Tech Transformation. Please.
Thank you. Hello, everyone. My name is Mutia, and I'm a tech lead and CTO at L'Oreal for an entity called Tech Accelerator. So thank you for having me. It's an honor for me to speak in front of you today. So today I'm going to walk you through our journey of implementing all the DevOps approaches to actually improve our delivery processes and our products. So this, I will start by giving you just a glimpse on the context, on how the situation was before and why did we do this. I will present you the DevOps architecture that we implemented. Few glimpses also about how we implement Terraform, how do we use it, how do we test our applications, different type of testing, and also what else did we automate actually to be in this situation where we are today. And I'll give you a few tips and takeaways at the end. So just for the context, so L'Oreal started actually a transformation program that is called Beauty Tech 3 years ago. So the aim was actually to not only provide products to our consumers, but also services, and to use technology actually to transform the company in both ways, actually, for employees, by giving them a few tools to improve their daily life, actually, and for consumers also to provide some services coming with the products they're using. So this transformation program actually gave birth to two teams called the Tech Accelerator. One of them is the Tech Accelerator Solutions, where we build systems for employees of L'Oreal. And the other one is called the Tech Accelerator Services that builds services for consumers. So the Tech Accelerator Solutions is providing more than 11 global products today. I'll not go through all the numbers, but it's a team that is growing, and now it's providing solutions on 3 different locations in Shanghai, in Paris, and in New York. And the Tech Accelerator Services is providing actually products for the users and the consumers. And it could be, for example, solutions for skin diagnosis, for virtual try-on or things like that. It's something that was built with a startup that was integrated into L'Oreal called Modiface and based in Canada. And we're serving tens of thousands of clients all over the world. So just to give you a global picture about our technical stack to better understand what I'm going to tell you after this. These are the technologies that we are using actually building our products. The main thing that you should keep in mind is that, for example, we're 100% cloud, so we're a partner with Google Cloud. So the applications that we're building are on Google Cloud. We're using Terraform for the infrastructure as code. Most of our products actually are AI-based, so we're also building algorithm with Python based on Vertex AI. There is an ML platform of Google Cloud Platform. And the orchestration tool that we're using for CI/CD and deployments is Cloud Build, which is not really known actually. Who, by raising your hand, already heard of Cloud Build or used it before? Told you, it's not really known. So it's the native CI/CD solution of Google Platform. And since we're 100% deploying everything on Google, it didn't make sense to go get another technology for CI/CD neither. So what was the situation before? When I arrived to this team almost 2 years ago, we made a global assessment, and we realized that we didn't have a lot of things standardized, and in different projects we had different ways of building things, different technologies. Sometimes the 2 teams were working on the same thing without knowing. The technical setup of a project so that the team can start building took a lot of time, weeks, sometimes months. And there was a lack of control and validation when people are pushing codes or deploying to a production environment or something. And of course, not everything was automated, and not that much actually. So the DevOps paradigm was not really implemented everywhere. So what we decided at that time is to concentrate on 3 main areas: application development, delivery, industrialization, reuse, and modularity. When I talk about application development, it's mainly how I act on code, how I secure how people are developing, how I control what people are pushing into my repositories. The delivery industrialization is more about how I automate the deployments into my environments. What is the workflow? What are the tools that I'm using? What are the artifacts? How do I version it? For the reuse and modularity, it's more to avoid that different projects are reinventing the wheel every time, and build our architecture in a modular way so that it could be easy to evolve and make those modules available for people who might need them in the future. So after this, we mainly concentrated on the delivery industrialization because that's where we had the biggest gap to achieve. So what we did is that we placed ourselves in a mindset where we decided to automate everything that we can so that we can concentrate on what matters. What I mean by that is that a lot of people in my team, for example, data scientists, used to waste a lot of time on deploying their algorithm to production because they didn't have any workflow or tools to do it. So they were spending more than 40% of their time on topics that were not their expertise, actually. So that's a waste of time for a data scientist that is supposed to be focusing on creating a value algorithm. So let me show you how did we architecture this. So first of all, as I told you, we are 100% on Google Cloud. So the first thing that we did is how do we want to architecture our Google Cloud projects? So we decided that one project on Google Cloud is equal to one environment. We at least will have per product 3 environments: development, QA, and production, but that's just a minimum set. You can have more if you want. And since we're using Terraform to templatize everything, you can pop as many environments as you want and destroy them when you want. And the third project is a transversal one that we call DevOps project. And there you have all the transversal resources that you use for your CI/CD chain, your artifact management, secret management. And from that project, you will be deploying applications, but also infrastructure into your different environment. Second thing, we also standardized the way of creating our repos. So nobody can create manually a repo, and nobody can create a repo from scratch. So we built templates, and those templates are actually the base for everything because everything comes with it. We have at least 3 types of templates: the web applications, the data and AI repo, and the EAC is infrastructure as code, so mainly Terraform. And those 3 templates are used to pop your project repositories. So this is stored in one GitHub organization for the use cases, meaning the applications, the business applications. And we have a second organization that is used only for modules. So where you can build JavaScript modules, Python modules, or Terraform modules. And of course, every type of these repo is created from a template also. So nobody's creating it from scratch. So what we decided also is that the modular organization, all the repositories in there are internal, meaning that you don't need to authorize anybody to access your repo directly. You just need to add them into the organization, and then they can see all the modules, because that's the point of having modules, is that everybody can be able to use them. So as I told you, nobody can create a repository manually because we want to centralize that, because we want people to respect the fact that we want to create them through templates, but we don't want to be 2 or 3 person responsible for creating those repos and setting all the branch protections, the code owners and everything. So what we did is that we built a service called Repository as a Service, which is actually a central repo that is visible by everyone. And we made repo creation made as code. So it's mainly Terraform code. Sorry, because you can't see the snippet of code there, but I'll zoom on it later. Anybody can come here and make a pull request on this repo, saying that he wants an infrastructure as code repo, he wants to add this team, and he wants this and this branch. So our only task as a central team is to validate or to comment his PR, but once it's validated, then it will pop all the repositories that he requested by writing his PR. So this means that something that used to take us like 20 to 30 minutes to do, we'll just validate a PR to do it, and everything will be popped as we standardize it and as we designed it. Just a little zoom on that PR. So as I told you, you can like write the name of your repositories, the description, the users that you want to authorize. You can also create teams. We can't see it here, but you can set your branch protection. You can set your GitHub website for documentation. You can do everything actually. You can do manually through the Terraform GitHub provider. So that was for creating our repository. So now I'll zoom a little bit on Cloudbuild, because as I told you, this is our main piece of the DevOps architecture, because it's our orchestrator and our CCD. Since it's not a really known solution, I'll give you a few information about Cloudbuild. So Cloudbuild is built for execution on GCP. It's using actually container images to build your application and deploy them or test them. And any pipeline that you design in Cloudbuild is a YAML file, like mostly all the solutions of CI/CD, and it's triggered by an events or triggers that you design yourself on GCP, and that trigger can be a PR, it can be manual, it can be just a push to a branch. So you decide whatever you want. And of course, every pipeline is built of different steps. The only difference is that for Cloudbuild, actually, every step is a different container, and that container is executed on the workspace system. So nothing is persisted between steps. That's the main thing that we should keep in mind, is that you can't use an output from a step 1 to as an input for a step 2. So this is the main constraint that we had to deal with when we started using Cloudbuild. Another thing you should know is that those templates that I was talking about comes with this design already implemented. So it's a basic one, nothing really, really advanced here. Is that we decided to build our deployment model based on a branch model, not a tagging model. So a developer, when he's pushing code, he will be having a feature branch, pushing it to, making a PR to push it to development, and then it will deploy automatically to the environment. And if needed, he will make a PR from development to QA to test his application in QA. And then from QA, we will make the production push by merging the QA into master. So just a global glimpse about what's Cloudbuild central, why Cloudbuild is centrally in our DevOps architecture. This is summarizing everything I told you. Just 2 things to know more is that we're using SonarQube for code auditing and testing for functional testing, but I'll zoom a little bit on that later. And everything in there is fully automated, except the fact of building this chain actually. So there is a Terraform plan and apply that are made manually by the central team that will pop your DevOps chain, and then all the teams are autonomous to build their application and infrastructure. This is just an example to what a CI and CD can look on Cloudbuild, but it's a YAML file, nothing pretty different except the fact that I told you the steps are pretty independent, and few other tips that I'll let you know about later. So, as I told you, the fact that Cloudbuild is a specific solution to GCP, it comes with its own problems. One of them actually is that, for example, you cannot operate any conditional filtering when you're building your pipeline. For example, you cannot decide that you're executing this task only on QA or development. So you need to use a bash script integrated into your pipeline to make that happen actually, or to switch just the entry point by default, because sometimes it's not suitable for what you're trying to achieve. The second thing you should know is that by design, Cloudbuild will use default service account. And what we recommend there is to build your own service account actually, and give it only the authorization he needs to deploy the infrastructure or the application you're trying to push. And the last point is about the environment variable. So these environment variable can be used through different steps, but the thing is that when you're trying to input a variable from the outside of the pipeline, it's not persisted through the steps, as I said. So we should use what we call a substitution variable that you can declare, but the $, but it's not, you cannot see it here. But that way it will make you solve the problem of persisting a variable between different steps in your pipeline. So that was about Cloudbuild. What about Terraform? So how do we deploy all of this? So this is the global architecture of how it works. It's actually a classic workflow. We just decided that for deploying infrastructure, we're going to apply the same life cycle as for applications. So we have this infrastructure as code repositories. DevOps people can push code to there with a PR, and then it will trigger a pipeline. That pipeline can be an apply or a plan job on Terraform. It will pull modules from our organization dedicated to modules and then deploy them into the project that you're targeting. So we're not writing Terraform codes for resources. Actually, we mainly build modules and people are playing Legos with those modules. So that way, we're sure that everything is standardized across our applications. This is just a glimpse of how Terraform repo looks like. We decided to separate resources in protected, DevOps, and applications depending on their life cycle. Application is something that is going to change often, like your services, your databases, something like that. Protected are the life cycle that are pretty long, like the network, the security, the IAM that you're configuring. And then all these resources will be instantiated by the environment folder. So you have one folder with the TFVAR files in each one. Few tips to keep in mind for Terraform that was pretty useful for us, but that we learned. So always a remote state and version state, because versioning your state make you able to revoke something you already did or to restore the state that you wanted before. And remote will prevent you from working locally when you're a multiple team working on the same infrastructure. Use templated modules, standardize a Terraform provider, because sometimes the version of your provider is not the same from a stack to another. And the last point is something that saved us a lot is when you have a new resources coming out, whatever your cloud provider is, sometimes Terraform is not providing that resource directly. So we use a local exec by Python, and we have like a condition to make it re-execute at every plan or apply, so that you're sure that that resource is updated. We make the plan jobs only on PRs, but the applies, we considered that we need a human apply for deploying the infrastructure, because on production, for example, it could be an action that is pretty dangerous. Sorry, I don't see this. And the last point that I wanted to talk about is during your jobs, actually, for example, when you're building your apply job, we always include a plan that is memorized, and then you're sure that your apply is taking that plan job and not something that was updated by another colleague, for example. just running quickly through the workflow of testing. So I told you that we use SonarQube for code auditing. So we built two workflows. One, when we are in an environment like development, and we don't want to break the pipeline with when the gateways are failing. And another one, for example, for production, when we want the deployment to be broke if we don't pass the gateway. And this is implemented as a step directly in our YAML file in the cloud build pipeline. Same thing for functional testing, but this is something that we're still improving. It is a step that we execute only for QA, but we're still trying to figure out what is the right workflow. Are we deploying an application on QA, executing the test, the functional testing? We use a solution called Test Team, and then rolling back if the tests are failing, or are we deploying a side environment where we execute our tests, and then if it's okay, we deploy in QA? Two different options. So what else did we automate? I heard somebody this morning talking about how AI is going to change DevOps. So we currently are using GitHub Copilot. It helps a lot with productivity because actually 80% of our code is suggested by Copilot, and you're just trying to improve it. We use a plugin called Chat Cody that you plug into your repos, and actually it's reviewing your PR yourself. But the next step is to give it the right to merge the PR and approve it if everything is okay. But we're still not there. It's still in a beta version. We use the PandaBot for the security breach, and ServiceNow is mainly used for automating tasks like creating a new GCP project, granting access to somebody. So here we are now with when we're trying to build a new application. These are the main steps that we're having now. And it's something that is going pretty quickly today. That took a few weeks before, and now it's taken less than a day, maybe 2 days. And these are the only manual action that we're doing. Everything else is automated. So what did we gain from this? Actually, is mainly our technical setup that switched from weeks to days. The release frequency, of course, we're deploying a lot today compared to before. Fault tolerance, because our systems, since they are standardized, are more fault tolerant. We have a better code quality, and of course, we reduced our infrastructure cost and also our carbon footprint. That's something that is pretty important to L'Oréal. This came also with a lot of other technical building blocks. I'll not go to the details, but it wouldn't work alone, actually, if we didn't build all of this ecosystem. And the ecosystem is also with the teams. Michael Feathers was talking yesterday about being not an isolated team, but acting like if you were on your own. That's something we applied a lot, but when you are part of a global big company like L'Oréal, you have to work with other teams like security, tech factories, or architecture. So that's what we did, and we also have a lot of partners that were helping outside of L'Oréal. So just to summarize the story that I was telling you, actually everything is not a matter of technology. You can automate whatever you want, reuse whatever you want, and scale your products. But for me, something that I learned is that if you're not having a mindset switch in your team and a cultural switch in the way you're operating, this will not succeed, actually. So the human factor is as important as technology. So I'll leave you on that. Thank you very much for having me. And if you have any questions, I'll be around.
Thank you very much, Mutia. If you have any questions, please maybe after that. So the next presentation will be starting from 3 p.m. So please back short. Thank you very much. Okay, we are starting our next presentation by Callum. The title is How I Made Prometheus Remote Write 60% Cheaper in 1 week.
Hello. Okay. Hi, everyone. My name is Callum. I'm from Vancouver, Canada, and I'm a software engineer at a company called Grafana Labs. Currently, I work on Loki, which is a log storage system, but I'm also a member of the Prometheus team, and I maintain Prometheus Remote Write. So today, I'll give you a quick overview of Prometheus and the Remote Write subsystem and how I made it cheaper. So yeah, again, an overview. I'll go over what what Prometheus actually is, what it does, the use case for Remote Write, and what I've changed within it, and then why was that change actually important. Yeah, so just so that everybody has kind of the same base of understanding, what is Prometheus? The shortest definition is that it's a pull-based metrics or time series monitoring system. It also provides alerting. There's a number of client libraries in various languages, Go, Java, C++, etc. And you would include these client libraries in your code to instrument it with metrics. You can also use these libraries to build things that we called exporters, which are basically ways to expose some third parties' metrics, so like MySQL metrics, as Prometheus metrics. And then Prometheus comes along and gathers the metrics from your application and stores them in its time series database. And then you use something like its HTTP API or a front end like Grafana to actually query those metrics. So I should clarify what I actually mean by pull-based. There are kind of two ways of getting metrics into a database. And the one historically used more often would have been push-based, where your application is configured to know where you want to store metrics. Maybe it's your Graphite server, something like that. And then as your application is going along, when something interesting happens, you tell it, send this metric to that location. Pull-based is basically the opposite. Your application includes one of these Prometheus client libraries. That library is responsible for keeping track of your metrics in memory. You still have code that says, hey, something interesting happened. Please update the value of this metric. But rather than sending it off to where you want to store it, Prometheus is configured to know where your application is running, and it comes along on some interval and grabs all the metrics for you. So this is kind of a basic deployment architecture of Prometheus. So we'll go from left to right. At the top on the left, we've got our own applications, maybe some web app and an API gateway. They've included the client libraries to expose metrics that you care about. So error rates or business logic, something like that. We're also running some third-party software, maybe a database, some kind of proxy, and we can use something called Node Exporter as well to get system-level metrics from our operating system. So in this case, if we have a bunch of Linux containers, we can use Node Exporter to get the metrics from those. Next, in the middle, we have collection, storage, and processing. So this is where Prometheus itself lives. Prometheus takes configuration to know where you want to gather metrics from. We call these things targets. And so in this case, let's say that this diagram we're looking at is a Kubernetes cluster. And so we'd be using Kubernetes service discovery to know where all the things are, where the pods are, right? We can also use that same Kubernetes service discovery integration to find all the nodes in our cluster and grab the metrics from Node Exporter. Initially, all the metrics that Prometheus collects are stored in memory, and then eventually, every so often, they're persisted to disk in, it's hard to read, but TSDB right in the center there. And finally, on the right, we have querying, dashboarding, and alerts. So like I mentioned, you can use something like Grafana to actually visualize your metrics and make some use out of them. And then Prometheus can also generate alerts as well and send them off to this thing called Alert Manager to deal with deduplication, grouping, and routing to something like PagerDuty, for example. So to understand the later description of Remote Write, it's kind of useful to understand Prometheus's exposition format. So this is actually the text format that Prometheus sees when it goes and asks your application for its metrics. Metrics are organized into groups by their name. So the white bit on the left of each one is the name. And we call these groups a metric family. And then under each name, under each family, we can have a set of labels. So these are basically like additional metadata that helps you identify a time series. In this case, we've got like the HTTP method and maybe what the status code was. Finally, on the right, it's a little hard to see, but you've got the actual integer value for whatever that metric was. So more definitions really quick. I'll refer to this whole thing here as a metric. First, on the left, we've got the metric name. In the brackets to the right, we've got the labels. Labels are composed of both a name and a value. And it's important to note that both the name and the value are strings. And then finally, the actual metric value on the far right. And the metric value in Prometheus land is a 64-bit floating point. So what is remote write? This thing that I'm claiming to have made cheaper. In the earlier diagram, in the kind of base level use case for Prometheus, we've got a single cluster, right? But Prometheus by design doesn't attempt to solve for something like high availability or horizontal scalability, right? So you can keep throwing a bigger ECS node at your Prometheus instance, but eventually there isn't a bigger node, right? Eventually you're gonna run out of RAM. You don't wanna throw a bigger disk at it, it's too expensive, et cetera. So what do we do at that point? And also what do we do if we have tens or hundreds of Kubernetes clusters, right? Ideally, we want a way to query the metrics from every environment at one point, rather than having to query each one individually. So we kind of have two options. The first one is we can deploy some sort of proxy that fans the query out to every environment that we want to know about, or we can store all the data centrally. And that's where remote write comes into the picture. Basically, remote write gives you a way to collect all of the metrics that Prometheus is ingesting and send them off to somewhere else, probably a different network. And there's lots of different implementations of the receiving end, but they probably provide things like faster querying by being a distributed system or multi-tenancy or additional security, something like that. One important note, and this kind of ties into how remote write becomes expensive and why it needed to be cheaper. The protocol that is used is designed to be stateless. So there's no tracking of state, there's no handshake, something like that. The intention was basically that the receiving side of the protocol was as easy to implement as possible. And we wanted to grow the community as big and as fast as we could. And so making it easy to implement on the receiving side meant that essentially anyone could do it. And finally, the protocol is using compression. It's using something called Snap. So like I said, there's a whole bunch of receive side implementations. Lots of them are open source, like Grafana's Mimir project. There's also Cortex and Thanos, which are both Cloud Native Computing Foundation projects. Cloud providers like AWS and Azure and all of them, they all have some kind of remote write receive implementation. And then a lot of the open source projects are actually built in Go, so they're using the same packages that Prometheus has already written. And so they, out of the box, support the same query language because they're using all the same code, right? So here we've got a really, basically the same diagram. All that's changed is the stuff from this kind of yellow line to the right. You can think of that as essentially a network boundary. And so our single Kubernetes cluster is now using remote write from its Prometheus to send all of the metrics to a remote write receiver somewhere else. And you can connect Grafana to that remote write receiver because it's probably supporting the same query language. And as far as Grafana is concerned, it's just a Prometheus instance, even though it's really something else. So at this point, you're probably wondering what's the actual problem, right? How is this thing so expensive, or why did it need to be cheaper? So I'll use my own company as an example. At Grafana Labs, we have this thing, Grafana Mimir, and we have this central deployment that we use for all of our production metrics. So there's one place that anyone who's on call has to go to see the metrics for the thing they're being paged about. And when I started investigating all of this, how we could improve it, we were writing half a gigabyte per second of metrics data to that central storage. And remember, that's half a gigabyte per second compressed, which ends up being about 1,200 terabytes a month, maybe a bit more. So storage is relatively cheap with cloud providers. It's definitely not the most expensive thing they charge you for, right? Where is the cost actually coming from? The main thing I was concerned about was the actual networking cost. Cloud providers charge you for data that leaves their network and goes somewhere else. And that could be leaving their network and going to one of their other networks. It doesn't necessarily mean that it's just leaving their network and going anywhere, right? That same network egress cost is actually relevant to our customers as well. So this central deployment that we use to monitor all of our own systems, we actually also provide that as a product for our customers, and they're going to have to pay to send that data to us as well, right? That's an additional cost that they incur on top of whatever we're charging. So, not to get too technical, and it's a little hard to see, unfortunately. This is basically the code definition of what the protocol format is. You can basically think of this as the packet definition. It's this high-level object called a write request. And the interesting field as far as the cost is concerned is this thing called a time series. There's on the left this keyword repeated. It basically just means that that field can appear more than once, and the library we're using to actually marshal and unmarshal this will handle it for us. So this is the time series object. The important thing to note is basically you can have essentially an infinite list of these things called labels, which are those metadata things that I showed you earlier, HTTP request, type, and status code, and all of that. And like I mentioned, both the name and value for a label are strings. So maybe you can kind of guess where the cost is coming from. So basically what's happening is we're duplicating a whole lot of information over the network. If we take the example earlier of that HTTP request total metric, for both these two metrics, one of which has a value of 1027 and the other one a value of 3, they both have different status codes with the same method. There's a whole bunch of strings that are repeated. Method is repeated twice, post is repeated twice, code is repeated twice. The actual name, which internally it's just an implementation detail, but the name is another label. Those are all repeated twice, even though they have essentially the same string value, right? And this is true for every single metric, every single unique floating point value that ends up in the write request. If we had 100 of these and they just had slightly different end values and slightly different label values, we'd be repeating the strings 100 times or more, right? So how can we reduce the amount of data that remote write has to send, but still have the receiver be able to actually accurately recreate the data that you care about, the metric you care about on its end, right? And remember that we're already using compression. So luckily there's smarter people than me that I can steal from. You might already be familiar with concepts like string interning or a symbol table. The idea here is relatively simple. We basically have a structure that we can insert a string into once, and then in the future check to see if that string has already been inserted, and if it is, just retrieve an ID for it, an integer ID. So what we do going forward is, rather than repeating these strings within the actual packet, the actual network data that we're sending, we have a table once for each write request, and the label, name, and value strings are just replaced with these integer IDs. And even if we're duplicating integer IDs a whole lot within the write request, that's much less data than strings. Like each character in a string is 4 or 8 bytes, depending on the language and all that, whereas an integer might be that much total, like 4 or 8 bytes, right? So here's the new, again, it's a little hard to read, the new high-level object for the protocol. It's called write request with references, basically. And the interesting thing is that down here at the bottom, we have the new table. It's basically a map of a integer value to a string. So it's a way to take a reference ID, some integer, and look up the string that's associated with it. And then the top level time series is also now a thing called reduced time series. So here we have the new reduced time series object. All that's really changed is the top bit labels is now a thing called label ref. Down on the bottom left, you can see that the name and value are no longer strings, they're just integers. Yeah, unfortunately, again, it's a bit hard to read, but down here, this is the actual code definition of the data structure. It's basically just two maps, one of which we use to see if something already exists in the structure. And if it does, return the reference ID. And then if it doesn't, we insert into both maps. So what did we actually save, right? So before I mentioned the network egress costs, right? A certain amount of bytes, in our case, 1,200 terabytes per month. So that's what we'll look at first. Prometheus is nice in that we write our own metrics into our own application all the time. So for remote write, there's a metric that measures the amount of bytes that it's sending. I saw with some configuration anywhere from 12 to 65% reduction in sending the same amount of data that I was sending before. The same amount of metrics data, not the bytes over the network, right? So the network byte size was reduced by up to that much. And the reason we can see such a wide variance is because basically remote write has configuration where you can tell it how much data to batch together before sending. And essentially the larger the batch size, the more strings data you're deduplicating, right? So again, it's probably, oh, darn. It's usually easiest if you can visualize something, but unfortunately it's not showing up very well here. Basically, this is a graph of that metric I was just talking about, the bytes rate for remote write. There's two different lines. The top line is Prometheus running the current official version of the protocol. The green line below is the one running my new modified version. All the way on the far left, we have the default configuration. That's where we're seeing like 10 to 12% reduction. So on the left, we've got like 24 megabytes per second versus 21. And then on the right, I've basically 10x'd the batch size. It's now 5,000 instead of 500. And the default Prometheus is sending 16 megabytes per second, whereas my new version is sending 8.5 to achieve the same result in the receiving side. But what about the actual cost, right? How much money do we save? Yeah. The short answer here is that unfortunately it's basically impossible for me to tell you an accurate answer for two reasons. One of which is cloud providers don't really give you a nice itemized list of your network bill. When you have a network egress cost, they basically just say, you sent X number of gigabytes from EU West to North America. Here's your bill for $1 million. Thanks. You can't see that, oh, this individual Prometheus instance in this Kubernetes cluster sent this much, and here's the bill for that. And the second is because, again, there's people that are much smarter than I am, and they're doing these things like network peering, or they've got a nice backbone between two different Google data centers, for example, right? And so as far as you're concerned, it's technically network egress, but on Google's end or whoever your cloud provider is, they're basically detecting that, oh, you're sending from one of our data centers to another one of our data centers. And they say, oh, okay, then you basically don't pay anything, or you pay very little. So you can't really look at the amount of data you're sending and their official pricing page and guess with any accuracy as to what the cost is going to be. So what's next? Currently in Prometheus officially, there's only one version of the protocol. And it wasn't until very, very recently, like in the last 6 months or so, that we said, hey, this version, it's officially 1.0. It basically was for a long time, but now it's official. And because it wasn't until very recently that we had this official 1.0 of the protocol, we don't have a way to request or enforce usage of a different version. And in a big or open source project, it takes a while to decide on how you want to enforce all of that. The last little bit is that this new version of the protocol, it's sort of a little bit of a breaking change. It's like the least breaking change that you could make to the protocol, but it is technically still a breaking change. So it would not be the default probably until a new major version of Prometheus. Prometheus is currently on a 2.x 240 something. So it probably wouldn't be the default until a 3.0, which there's been ongoing discussions about for a while, but who knows? It's an open source project, right? So I'm still working on all of this. It's ongoing. People are excited about it, but it's not my main job. As I mentioned, I do it on the side. My main thing is logs aggregation. But this is the pull request on GitHub. If you're interested in the pull request, there's also a link to the design doc where we discussed alternative ways to make it cheaper that we'll probably also do in the future. But this was essentially, like I said, like the least breaking change and a big gain for 1 week of work. This was a hackathon project. Yeah, actually don't know how much time I have, so I don't know if we have time for questions. After? Yeah, okay. Yeah, I'll be around, so let me know if you have questions, but if you want, there's also information about where to get Prometheus community, you know, documentation and ask questions in general about Prometheus as well. So let me know if you need any of that. Thank you.
Thank you very much, Callum. Okay, so the next presentation will start from past, so from 3:30. See you again later. we'll be starting our presentation by Michelle. The title is Code Your Cloud Infrastructure with Jenkins and Terraform.
Welcome to my session. Thank you very much for attending. I'll try to speak as slow as I can because the translators have to keep up with my talk. So I hope it doesn't bother you. My name is Michel Schildmeijer. I want to ask you to pronounce it. I'm Dutch. I'm from the Netherlands or Holland or Hollanda or whatever they call our country, but officially we're called the Netherlands. And I'm very honored to be here in Tokyo. It's my second time. I was here before COVID in 2019 as well. So yeah, I enjoy the city, I enjoy the country, and I enjoy the people, seeing new people other than those who are living in my city or in my street. So that's very exciting. Okay, my mother always told me first introduce yourself to someone you don't know. So this is a little bit about me. I won't dive into much deeply. I was born in 1966, sorry. And I went to school and everything in high school. And then I started studying clinical pharmacology for a few years. I joined the army as a pharmacist, and then I ended up as a clinical pharmacist in a hospital and doing some industry work as well. But then I decided to switch to IT because I developed a system for medical records at that current job at that time, and I got very enthusiastic and switched to IT. And here you see some of my things which I've done and which I have achieved. I'm an Oracle ACE director. It doesn't mean that I'm an employee of Oracle. I don't have to do a commercial talk of Oracle, but I work a lot with Oracle technology. So, and it's more like an evangelist, an advocate around Oracle technology and other technology as well. And in 2022, I became also part of the cohort of the CDF ambassadors. So, well, in this year I didn't apply because I don't have time to contribute, but yeah, it was very fun to do at that time. Okay, the topics for today, I have 3/4, so I hope I'll manage, or maybe I'm early finished, so I don't know. Something about DevOps challenges, infrastructure as code, CNCF landscape and the relationships, and then a little bit deep dive into the components which I'll be talking about. So where I come from, I'm not a hardcore pure developer. I'm more from the ops area. So one of the things, coding is not something what's basically a thing for ops people. There are people who are good in scripting and everything and think logical, but coding is not really a thing because also they want to have stable environments, not too much change. Production has to be always running and has to be available for the customer. So from that perspective, I created this presentation for customers or for my own team as well to tell a little bit more about infrastructure as code and what it could bring to the team, to the customer in terms of flexibility, availability, standardization, and of course, if you talk to a business manager, what's the value, added value for me? So I'll try to explain that a little bit more in the coming slides. So there are some DevOps challenges, and if I picture this to people who don't know anything about DevOps, then this is the slide I use because everything, the key aspect around DevOps is continuation and automation. Automate everything as much as you can actually. So your build process, your testing, and your deployment, and even also your monitoring has to be automated. So automated is a very interesting and a very important aspect of your DevOps work methodologies. So to achieve that and to shift from a traditional siloed way of working with an infrastructure team, with a developer team, with a database team, and maybe a middleware team or an technical application administrator team. You have lots of teams and lots of different expertises. I try to use some kind of a model, a framework, which is developed by Forrester, and it's called the CALMS model. And this CALMS model talks about how you implement from traditional service delivery, like ITIL before, for instance, or Prince2 project methodologies, to more like a modern service delivery. And there are a lot of change types which you can address, and two of the important things for DevOps and for CI/CD are those two. So like automation, you want to skip every manual process as much as you can, less human interaction and more flexibility and better lifecycle management. If you come from a organization with a lot of legacy and with a lot of siloing in every layer of your IT landscape, then it's really a painful process to undergo, and it takes a lot of time as well. But the investment pays itself in the end. So, and if you look at the DevOps ecosystem and the requirements which you have to think of what you need for a team to become a DevOps team. So first of all, bring in the culture to the organization, for instance, and then try to have something like version management. I know developers, it's more like a common thing, but if you look at ops people, version management, okay, yeah, I have version 1, I write it down somewhere, but they don't have any repository in more like in the starting phase. Automating builds and tests. Well, if you look at infrastructure itself from a traditional way, infrastructure people, I come from a time where I still saw the iron. I connected the plugs in and everything, and I joined a team for a banking application where we managed the entire infrastructure, including all the hardware as well. Sorry for that. But nowadays, you don't even know where your application is running. Somewhere in some cloud or at some data center, at some part of hardware, you don't know anything about that, and you don't need to know actually anymore. Just be precise about your specifics, about resourcing, what you need, all those kinds of things. So all these topics here mentioned are important for your development and for your ops to be used, like continuous delivery and integration. You want to have some kind of a process which covers that all. Provisioning as well. So provision your infrastructure in an automated way, but also for your team, also issue tracking, code review, for instance, use some activity channel where you also can post all your infrastructures or your development cycles into, to have any clarifying things to show to other teams where you're at that moment. So if you look at infrastructure as code as one thing as part of your automation process, then why should you consider infrastructure as code actually? Well, one thing is that when you do infrastructure as code and you don't touch the iron anymore, and even within cloud, it's just something which you can click together in a console or wherever, and you have to treat it more like a software component instead of a commodity somewhere running in some hardware data center or in the cloud. So you version your infrastructure as well as same as a developer version its application release. You can automate your infrastructure provisioning process, so you can run it multiple times, doing a configuration change, for instance, all through the process itself. So it enables, of course, the agile methodology of working. So your team can be, it doesn't take any 2 or 3 or 4 weeks to spin up a new server or new hardware, because the infrastructure team is involved in your team, and they also see the importance of delivering a fast new infrastructure component. Standardization is also a very important thing. So be consistent on every stage which you have in your entire process. So this is a slide I would show to business people if they ask me what's the business value of doing this all, and taking a lot of work migrating all these on-premises to the cloud, or these legacy into more modernized infrastructure and application environments. So these are some the slide which I would show to a business manager, for instance. So investment space for itself, actually. If you look at infrastructure as code, it's already there for some time, and one of the most well known to me actually is Puppet. Puppet is a tool which is being used for over more than 10 years now for me, and Puppet is a tool to infrastructure automation with declarative language. So it's readable for a human. It's not something to read before go to sleep, but you can take out and you can understand what's being meant. It's model driven, so you can use different models, modular. It uses a state language to control the state of your infrastructure. So you only have to change the components which need a infrastructure change. You have some tools like Factor, which is a key value store for discovery of your nodes, and it's written in Ruby, and it uses agents. So you have to install agents on every new node you want to deploy. So actually, it's a thick client. Somewhat similar to Puppet is Chef. It was 5 or 6 years or 7 years ago. It was very hot, but I don't hear anything about it anymore. It's being used maybe, but Chef is somewhat similar. Also uses Ruby and some Erlang language, and it uses the concept of cookbooks and recipes. So you take some kind of a cookbook and you take some recipes out of it and use that as a configuration as a whole. And Chef is agentless, so it uses APIs for node discovery. Like you can use OpenSearch, for instance, to with an API to discover new nodes in your infrastructure. And the last one, there are loads more, I think, but Ansible is one of the well-known as well. Also open source, and you also have a commercial version which is called Ansible Tower. Also declarative, and it's agentless. That's the important thing for this one. You need SSH access for that. It's written in YAML. The playbooks are written in YAML, and because of a lot of libraries underneath, you don't need as much scripting as in other infrastructure as code tools. So it decreases the need. So infrastructure as code with the shift to cloud native, with all these cloud native terms like containers, microservices, continuous integration. If you present this to an ops team, they will go and be flabbergasted and will dizzy their head. So we have to first explain what's in it and what's about it. Well, containers technology, which is packaged actually and rid of all the dependencies to infrastructure, and serverless is even more independent of your infrastructure, because then you start an application and you only consume at that time what you need for your serverless application, and that's it. And of course, infrastructure as code, which I will talk about, or I am talking about, is provisioning this programmatically your infrastructure as a software component instead of a commodity, hardware commodity. So to picture Terraform, I'm always visual, and I would like to visualize things. So terraforming, well, terraforming Mars is something everyone knows. Elon Musk wanted to go to Mars this year or next year, I don't know actually. But this is what you get when you enter Mars. There's nothing. It's just a desert and maybe some frost, permafrost somewhere where maybe some tracks of life are in. But this is an empty space and you have to terraform it. So let's say we have a cloud, and in my case it was the Oracle Cloud, but you can name any cloud you like, of course. Oracle Cloud is called Oracle Cloud Infrastructure, OCI. And then you want to put something in, some kind of a city or whatever, a community, which is called a compartment within Oracle. It's a separated, isolated component where you can put in every resources from your cloud. I expect AWS or Azure has the same concept with resource groups from Azure. That's a little bit of the same concept. In essence, all the cloud providers have somewhat the same concept. They name it otherwise, but the concepts are still the same. So you have to create networks because otherwise you can't connect to anything. Maybe multiple networks, of course. Maybe you want to have virtual machines in it. Storage you have to have in maybe databases. And well, let's do it something cool and modern for an ops guy, of course. Let's do Kubernetes and the Kubernetes managed cluster. So with that, you need a load balancer maybe, and you need some firewall because you need to be secure. I attended a security presentation front before this presentation, two presentations before my, and I saw all kinds of extra security measurements you have to take before you can say I'm secure in my application and in my cloud. So you can provision it to your users, your end users, and maybe you have some APIs as well. So all these components which are here are all able to be provisioned by Terraform. It doesn't matter what you have, what kind of component, as long as you declare it in your Terraform configuration, then you can build and create it. Of course, not necessarily automated in an automated way, but you can do it automated as well. If you look at Terraform, where it's coming from, Terraform is an open source tool, and Terraform is part of the Cloud Native Computing Foundation. Actually, the Cloud Native Computing Foundation is a organization which came out from the Linux Foundation, and they try to control all the new open source projects which are either open source or cloud native. And there are also members, and the tools which I discussed today are also part of the Cloud Native Computing Foundation. So Jenkins is one, that's an CI/CD tool, and of course Terraform. And for me, Oracle is also a member, as well as Microsoft, IBM, all the big parties are there. So Terraform itself, it's an open source tool. It's created by HashiCorp. It's compatible, that's the strength of Terraform. It's compatible with many cloud, and it has a lot of cloud providers. So yeah, you can actually use it almost anywhere on your own cloud as well. And it's compatible with the most operating systems as well too. So there are a lot of binaries to download if you want to try it out. So with Terraform, you can configure, actually for Terraform, the most important thing is to configure your end state. So Terraform needs to know what is the end state which I'm going to deploy. And that's the starting point for, it's a bit weird to say the end state is the starting point, but that's the starting point for Terraform to deploy the configuration to the cloud. And you can define it. You can define your infrastructure. You can also update it partially with modular approach, or you can destroy it entirely if you require it. It's also declarative, so human readable, and multi-cloud platform deployment is also, because every organization has multi-cloud, it should be multi-cloud ready as well. It's agentless as well, because it uses API, so you don't need any agent to be installed on any node. And configurations you can store on your version control. So that's also the approach of infrastructure as code, to version your infrastructure configurations. So if you look a little bit deeper into Terraform, you have several components within which makes the entire Terraform deploy process. You have some configuration files. You have providers, which you download actually when you do Terraform init. So you define your provider which you need for your cloud, and then if you execute Terraform init, then it downloads the provider for your cloud. Then you have the resources. Well, these are in fact the cloud objects which are actually provisioned to your cloud. Data sources, if you, for instance, have already a cloud and you have some parameters to consider, like a network which is already there, then you can put in extra information in those data sources around the environment which is already there. Then you have variables. You don't want to hard code anything, so you try and use variables, but it's more like the metadata variables which you put in. And then you can also generate outputs if you want to display anything for other systems for in your entire process, your entire CI/CD process, to provide information which other CI/CD process can use to go on with their CI and CD pipeline. So to obtain Terraform, it's just a binary which you can download. You can automate that as well. Within Jenkins, you can automate this. So download it with every new pipeline. And the provider from OCI, you can download it from HashiCorp itself, or it will be downloaded. And the other cloud providers, it's the same story, actually. So this is a basic workflow for Terraform. You have your client where your Terraform binary is running, where you execute your Terraform commands. And first of all, you need to set up the API access to your cloud, so it generates some security things. In this case, I've generated private and public keys to access my cloud provider, set up an API key on the cloud side, and use that one in my environment variables. Do a plan, an execute plan, because that's the basic of how Terraform will execute the configuration. And then you can run and apply. So that's a very basic workflow of a Terraform action. And then the cloud resources will appear if there's no error, of course. So the first approach, which I opposed to start with in my team, because they were fully unaware of what CI/CD was and how it worked, and also it took a lot of time to build it up, to build an entire CI/CD for the entire organization. So we started very small with a container, a Jenkins container. We did a Terraform installation. We set up a Git repository. I used GitHub for my own purposes, but of course you need a private repository and no GitHub, or you have to secure it very safely. So we chose the Terraform provider. We created our Terraform configuration files based on the documentation of Terraform itself, of HashiCorp itself. And then we already had Jenkins for the application builds and deployments. And we thought, well, our company already uses Jenkins, and you can also use, of course, if you run Azure, you can use Azure DevOps or any other tool for DevOps way of working. But in this case, we said, well, we already have Jenkins. We invested a lot in those things already. So why don't we use Jenkins also for cloud provisioning? So I thought that was a good idea. And the deliverables for us were that we wanted to have a virtual network, of course, and the route tables for internet and service gateways, some public and private subnets, some network policies. We wanted to have, in this case, we built a Kubernetes cluster. We wanted to have a public control plane subnet for access for the administrators on a a different subnet, of course. It was protected, so not public in sense of on the internet, but public for the administrators. And a load balancer for the application to access to. Later on, also we tried to use a bastion host and an operator host to get more security up front, and some network security groups, which I already mentioned. So if you look a little bit deeper into Terraform components, if you start up with Terraform, then you have a workspace where all the configuration files are in, and also the state if you have it locally. And during your Terraform executions, you actually merge your plan into your configuration. You merge it into an execution plan, which will be executed as soon as you initiate the apply command. So this is the basic setup we had. We wanted to create a Kubernetes managed server, and here you can see some of the Terraform files. And the most important ones were the main Terraform file and the Terraform TFRs file, which is in fact an implementation of the variables which you define in your metadata file, the variables.tf, and the variables are being injected into the Terraform TFRs file. And we also used some extra modules because we want to be flexible. An extra module like a Bastion host or some other extensions. At the end, we wanted to have a some kind of a enterprise way of working with Kubernetes, and this was a Kubernetes cluster built with extra stuff like Rancher, like some extra identity and access management tools with Prometheus, Grafana, and OpenSearch. Which we defined in our extensions module. But this made us very flexible because you could apply one of the configuration changes in your network because you wanted to add more resources to it. And with the module approach, you can be very flexible because you update only the stuff you want to have in your own branch, and then you merge it into the main branch if it's okay, and then you can apply the configuration. So environment variables already mentioned. These are in fact credential things and all kinds of stuff. It's advisable to store your credentials somewhere in a vault. Terraform has a vault solution itself, but also cloud providers has vaults which you can use and can be integrated into your Terraform configuration. So this one looks like a bit like the Terraform TFRs file, which are in fact a representation of the variables, which I already mentioned out of the metadata file. So variables are already set, or they represent parameters for configuration. They're more like metadata than the actual variables. And you can also define some Boolean types. Like if you don't want to have a like a Bastion host or something like that, then you can set the Boolean to false. So in this case, it's all very flexible. So you can see it in here like a let me see. Here, create a Bastion host. Default is true, but if you don't want this kind of thing, you can set it to false. Okay, next one is the provider. So in here you define your variables for your provider, and in this case it was OCI, but if you have AWS, of course your provider will be AWS. And if you do your Terraform init, then it will download all the things around that, and it will be injected into your Terraform configuration plan to be provisioned as a in this case OCI cloud configuration. And you have some others already mentioned, data sources for external components, which are not actually part of your infrastructure at that point. And you can add them and use them for extra purposes to be configured in to your entire configuration. So executing code, it's very easy and simple. Download it. This is the Terraform init command, the plan command for the execution plan which you want to use. And then you get a whole list of all the configurations which you won't have to read, but you can also store it somewhere if you like, if you want to read it. And then you can execute your code and it creates a state file. So the state file maintains the state of the configuration objects. So if it's created or is it maybe not created, and if it's not created, it can be there's no rollback mechanism within Terraform. So the only rollback mechanism in Terraform is to roll back your version to a previous one and reapply the state. So then only the changed objects will be changed as well, and then you can debug your code. What's wrong? What went wrong? And Terraform Graph, that's nothing. You can create something like a architectural overview of your Terraform components and the resources you built out of your Terraform plan. That's just more like a graphical representation. Sorry. So next, the Jenkins pipeline. So how does that fit into Terraform? Actually, very simple. It was also a very simple setup. With Jenkins, also you can build very complex pipelines, which all depends on each other and all glued together. But we started very simple with one basic thing: just provision the infrastructure in an automated way, in a semi-automated way, because the administrators, the operators, still wanted to have some kind of a control. So we built in some action item within Jenkins that they also could manually apply and manually destroy their infrastructure. So Jenkins itself, I don't know if you know it, but it's an open source automation tool, sorry. And it was initially always used for developing and testing and integrating your code into to the mainstream. Jenkins also, you have a lot of other CI/CD tools, especially for cloud, but also Jenkins itself also works into getting more integrated into cloud native things. And Jenkins acts as a cloud extension, but also within Jenkins itself, you can use a lot of cloud features as well. For instance, if you Jenkins makes use of slaves, which are in fact nodes somewhere else, and you can dynamically say with a plugin in this case, it was the Oracle Cloud. If I need more slaves to gain more performance, then I can create an extra slave in my cloud provider as a support for my entire Jenkins environment to get better performance in deploying and provisioning everything. So this is how a Jenkins Terraform CI/CD pipeline looks like, in essence. So first of all, I need to create a pipeline. In this case, I called it Terraform OKE with a number. I need to have some credentials like access to my GitHub repository or Git repository or a webhook or anything which you require to have access to. Then you need to read out your branch or your main version in this case, which consists of all these configuration files of your Terraform. But then you also need something called a Jenkins file, which is a representation of your CI/CD pipeline and the actions you perform within it. So if you look at this Jenkins file, all the actions, all the commands of Terraform are within it in a step. So every step is a process in your pipeline. And I already mentioned the administrators wanted to have some extra control. So I've also built in within Jenkins an action parameter where they could manually apply or destroy or anything they would like to do to get some control. So this is part of, I don't know if it's readable. Can you read it? Or no, I don't think so. In fact, this is part of the Jenkins file with the steps. I will show it later on. I will show it for you. So this is my GitHub repository. And here you see a very simple setup of a Jenkins. Oh, not there. Oh, I know why. I have to share it. Yeah, you can see it now. So this is a Jenkins file with some stages and some steps which you can use for your pipeline, actually. So here's a stage with an action which is called plan. So the plan of the execution can be done in here, and you can glue it all together into one process. If you have a nightly build, for instance, and you don't want to apply manually, then you can apply it all and do the execution as well, and then the end result can be in some output file or anything. And these are some of the other steps. And you can also enhance it with Groovy. Groovy is a language which is being used by Jenkins to add more parameters and variables for your pipeline. So you can also put in some kind of dependencies, if you like, in your pipeline, or say, I have a build X, which is applicable for application Z, and you can build it into your Groovy script. Okay, that's about it for me. Don't know if there room for questions.
Yeah. For like 8 minutes, you can have your questions.
Okay.
If anyone wants to ask.
Hello, thank you for the presentation. I was wondering if you have any advice on how to manage the state file, because once you have the state file, for example, in Jenkins, it will stay on that machine, right? If you get to lose it, it will be gone. I know there's some other solutions also within, for example, using console or something like that, or if you have the other approach, maybe back it up in a different way, or how to make it distributed.
Yeah, we haven't thought about that, but we were thinking maybe use a artifact repository, for instance, for that. Could be a case, but I don't know which solution there is in the market for that. But we thought about maybe use a Nexus repository for storing the state files, for instance.
Okay,
yeah.
Thank you.
Thank you so much for your presentation. I would like to ask like one question, especially like the thinking about like if the target infrastructure have to be like is immutable, because like if we think about like this is mutable machine, let's say like a virtual machine that's gonna cost like the Kubernetes cluster. Time to time we need to actually apply like the OS security patches, and then like unfortunately we can't really get like the full benefit of using like the Terraform as IAC, because it is not like immutable. It is mutable, and like we can't simply redeploy everything from the scratch because application is already on it. And at that point, like we have similar kind of like the concern in our work, and how you are actually considering about like where it should be actually adapted and where it should not, or like at least like the very first is the deployment or provisioning, better to using the Terraform to make it as a code, but later it's different.
I would suggest to just use it for configuration changes, because those you can roll back, as I mentioned, with your previous version of your code. So it's immutable, yes, but you can roll back everything you like, you provision. Yeah, and yeah, for software components, I would use a golden image, for instance, to be used as a starting point of your changes. Yeah, I don't know if it answers your question, but yeah. You're welcome. Thank you very much for your attention.
Thank you very much, Michelle. Okay, thank you very much, everyone. From 4:30, there'll be a closing keynote at the big hall over there. I think they are preparing right now. So once you're ready, please head to the bigger hall. Thank you very much.
The big hall will be in English, and this room